All right, let's get the. So let's look at the, since you guys talked about the pool ball, the pool table, let's look at that problem first. Let this thing come up. Oh, never mind. There you go. This is okay. Now he says, okay, well, it's trying to come up. It looks kind of, well, it is yellow. Okay, so it's yellow there. I was about to say something's wrong with it, but I didn't notice. So he claims, this guy is claiming, I don't know who this guy is, but this guy is claiming that the cue ball is 0.17 kilograms and that the numbered ball is 0.16 kilograms. So let's go ahead and use that. I don't know that that's true, and I don't have any devices to go over there and measure them anyway. Yeah. So not a whole lot, but decently heavier. Yeah. So let's go ahead and go with that. Okay. So let's first do a straight on impact. So you're sitting at the table, you want to hit it, and you want the ball to go exactly in the direction that you hit the other ball. And so I don't know why it bothers me to have a pen that colors just because I can. Maybe that's why I want this. So here's, I'll say the cue ball and the 8 ball, just I don't know why. But the cue ball has a mass, what did he say, 0.17 kilograms. And this is 0.16 kilograms. Let me double check that though. Is that what it was? 0.17, 0.16. Good enough. So let's first take the case where E is equal to like 1, and let's see what happens there. Now, I'm going to carry them first. Well, I'll go ahead and carry them the way they are. So if you had a perfectly elastic impact, let's say that the velocity here is, I'm going to just make it 1 meter per second. Actually, a meter per second is pretty fast on the, if you think about it. Well, yeah, I mean, you could make it go faster. And let's say that this ball, the velocity of 8 is, the 8 ball is nothing. So the cue ball is this. You're going to go across and hit it. You want to basically see what happens here. That light right there is reflecting right off on me. Here. Is that one? No? Oh, there we go. So, so you got two equations. You got mass of C, velocity of C, initial, which is numbered 1, but in thermo it's going to be I. Mass of the 8 ball, velocity of the 8 ball, initial, mass of C, velocity of C, final, mass of the 8 ball, or any other ball, velocity 8, final. Now, I'm going to go ahead and start in on this. This one is 0, means I really only have to consider on the left-hand side, MC, VC1. Thing is, I have to pick the oriented direction. So I'm going to say that's plus. So that's the positive direction. So that means my cue ball is heading to the right, which means I have 0.17 times 1 meter per second. And that's all I get on the left-hand side. So I get that, which is equal to, now I'll start filling in on the right. On the right, I'm going to have 0.17 velocity of the cue ball after the impact. 0.16 velocity of the 8 ball after the impact. And I really can't go any further than this. So I guess I could just copy it down Same thing. Oops. Velocity of C2 plus 0.16 velocity of 82. And from here on out, I'm sort of dead with that. So then I need to go over here and take a look at this. Now, I'm going to put a box around this because what I'm going to do is start changing things and see what happens. So I'll just, at one point, I'll just leave it as an E, if you guys are okay with that. So I have two different things in impact, the C and the 8. The final one ends up on the top, and it's organization, they flip on the bottom. That's what I'm trying to say. And I'll give you, after we do this problem, I'm going to do the basketball problem and show you another way to remember this. Okay, so what do I have? 8-ball initial, nothing. Cue ball initial, +1. So I can take this 1, move it across over here, and I'll have another setup. Okay, so what I'll have, it's a minus under there, so it's a -1. I'm leaving it as E right now. VC2 minus V82. I don't know either one of these yet. I think I'm going to change it. V82 minus VC2. Just because maybe that would be. So I have that sitting there. Because of the coefficient of restitution for the impact, I end up generating a new equation. So I guess one of the things I could do is say it's all done, and now I'm going to combine these two. If I combine these two, why did I draw that line across there anyway? Maybe I want to draw this one up under that one. If I do that, you know what? I think I'm going to do something to this equation first. I just noticed there's one more thing I could do to this equation, and that is divide it by 0.17. So on the left, I'd get this VC2 plus 0.16 over 0.17 V8. So I did that just so that I could clear this up, you know, and clear out that 0.17 there, because I don't have a coefficient here and here. Did I do that right? Did I write it? Okay, no, wait a minute. Am I seeing something? This one? Oh, I'm sorry. That's supposed to be a 1. Yeah, sorry about that. Yeah, so. Oh, okay. Okay. Yeah, so the way, okay, so since I made that mistake, let me spend a few seconds here. So if you have two impacts, say an A and a B, when you write it down, you just swap it. Now, you don't have to memorize this, by the way. And then these on the top is all the finals, and this is all the initial. Now, in this class, he likes 1s and 2s, and you subtract them. So that was my mistake right there. That should have been initial. So, yeah, sorry about that. And sometimes when you make a mistake like that, it distracts you from the rest. So now that I made that mistake, I left the E as a symbol right here. I'm going to bring up later and say, I'll look at this number later. But for the moment, I'm just going to leave it as E. I drew the 1 or a -1 up here because I have a minus here with this. I drew it up, and I end up with this one. And so I end up with this equation that sits here and looks like that. The reason I did this is because if you notice, I've got these clear coefficients here. There's a 1 in front of both of those. So if I could get a 1 in front of this one, that makes my life a little easier. So, so now what I'll do is instead of dragging it here, I'll drag it down there. What I'll do is I'll say, and I guess I could take the box off of it now. Yeah, I'll take the box off of it. I'll make a semi box. How about that? And then I'll put E. Well, I'll leave the box back on it. What am I doing? I don't know. And I'll say minus VC2 plus V8 ball. And then I'll add them. And if I add them on the left, I get E plus 1 equal to, what is that? 1 plus 0.16 over 0.17 V8 ball. Now, what I'm going to do now, I didn't bring up MATLAB, but this is a good case for MATLAB. M-A-T-L. I think, uh-oh, what happened? Is that it? The school is behind me about a whole year. I buy MATLAB at my house, and I've already got 2018A installed. But it's hard to maintain a lot of computers. A lot of work. So what I'm going to do is I'm going to do this. I'm going to go in and I'm going to say, okay, V8 ball after the impact is equal to 1 plus E over 1 plus 0.16 over 0.17. Okay, then I'm going to say the cue ball, and I'm going to get the cue ball, say, from right here, the equation from right here. So it's going to be the 8 ball after the impact plus the E. If you look at it, that looks kind of funny looking right there. Now, if I wanted to put it in there, I mean, I could put it in there. Here's the way I could do it. I just sort of do it this way. Here, I'll take these, slide them over, take this one, since that's there. I'll go ahead and take this, do a copy, paste it, move it right here. And there you go. So there's the velocity of the cue ball after the impact, if that makes sense to you. So what I'm going to do is I'm going to monkey around for a second in MATLAB. I'm going to say, I'm going to create a vector, call it E is equal to, I don't know, I'm just going to do like 3 of them. 0.95, 0.98, and say 1. So I'm going to do it for 3 different E's. So if you're used to doing this, it may make sense to you. VC, the cue ball is equal to 1 plus E, and then you got to divide that by 1 plus 0.16 divided by 0.17. Did I do that right? Plus E. So take a look at what you get here. Did I do that right? That doesn't look right to me. Okay, that does not look right at all. Let's look at the 8 ball, see what the 8 ball shows up. The 8 ball looks like that. That doesn't look right either. So I've done something wrong. Let's see if we can decipher. There's no way that this is correct. So and the reason I know it's not correct is, oops. Okay, wait a minute. Do what now? You got the same answer I got? Oh, okay. Well, something else is wrong with my math because there's no way that a ball can hit this ball with no velocity and it continue to have the same velocity. That just doesn't make sense. So let's see if we can decipher where I've gone completely awry here. And you might be able to see it before me, but that's okay. Okay, so let me review this part. Okay, so I've got that. There's only one oriented direction. So there's only a 1 here. So far, I don't really have to address any of these distances because, you know, that you don't know them yet. So I'm assuming them to go to the right. Okay, so this is the mass of the cue ball, mass of this, and did that. Okay, now didn't do this next part right. Drop the 1.7 under 0.17, 0.17, 0.17. I think I'm okay there. Let's see, what did I do wrong here? Okay, VC2, VC1. Okay, so I kind of said we were going to look at that later, but the impact, I don't know the final velocity of C2. I don't know the final velocity of 8.2. I do know this one's sitting dead still. I do know that one's going to the right. That's positive, like I drew up there. So that's positive, makes that negative. If I drew it out times the E, 8.2 minus C2. Okay, so am I good so far? There's got to be an error in here somewhere. I mean, it's just not possible. Do it now? Oh, well, okay, so what does this seem okay? C2, E2, C, 8 and C, initial. Okay, do that. C2, flop them, draw this thing down. Okay, wait a minute. And then, okay, oh, I think well, wait a minute. Let me make sure. Okay, wait a minute. This one? Oh, let's see. You're correct. Wait. Let me double check. If I draw this one over, draw that one over, yes. So I think we're okay. I'm still disturbed by that one though. Let's see if I can fix. Let me. Okay, so say that again. Okay, so wait a minute. Okay, now to this one bothers me. Okay, here's why. Just my numbers. Let's look at the numbers. If I looked at the V8 too, okay. Oh, yeah, you're right. You're right. Sorry about that. I was thinking the 8 ball. I was still thinking of the cue ball. This is the cue ball. This is the 8 ball. Sorry about that. Right. And that was where I was trying to go to. So, yeah. So the mistake I made was there. I think I'm okay here. So now let's do the MATLAB part again. And something happens. Let's see. Okay, so the cue ball, let's go back to the cue ball. The cue ball one was the one wanted to focus on the most. And what you notice is something like this. Now, looks to me, I can't remember, how did I lay them out? I laid out 0.95, 0.98, 1. So there's something that you see on the table, and you've probably seen it before, in which the ball hits the other ball and it stops. So let me do something different here. Let's say both balls weighed the same for a second. See what happens. See, this is to me, this is there's something wrong with the 0.17, 0.16. I'm not exactly sure. Okay, so you've seen this. You've probably done this at the table before. Have you done that before where you hit it, the other ball sits dead still? And so you can get that. But this other way, the two masses, you can't get that. Now, okay, let's see. Right. And the other thing too is if the two balls are real close, the cue ball in its travel, let's say they're far apart, as it goes across the table is slowly rotating it. Then when they hit, the cue ball has a little rotation, it'll roll forward a little bit. If they're real close to each other, the friction doesn't have a chance to start rotating the cue ball, and it bang, and it stops, and the other one goes on. And I've seen that before, but this is not showing it unless they're both the same weight. And so the other question is let's say I had them that way before, right? Let's reverse them. Now that, I don't even think that's legal because, oh yeah. However, if we're going to do that, let's do something to E, meaning, let's do this, 0.925. Well, here, let's do 0.9, 0.925, and a 0.95. Yeah, got to put the right. And we'll do the calculation again. And what you see is there's a possibility somewhere in here that if the reverse were true, you could have a less than perfect impact and then actually have the ball sitting dead still. So it's kind of a fine line in there. So my argument is maybe and I don't know, because we're looking at a very small mass difference. I don't know that I have the ability to organize enough people to go to the physics department, go over here, grab the cue balls, head off to the physics department, weigh them, and then come back. And it just might be too much for us. But we can go over there and see this in action. But in fact, if they weighed exactly the same, and if it were a perfect impact, that's what you would get for the cue ball. For the 8 ball, I have to fix my equation. Oh no, I don't have to fix it. I have to find it. Okay, this is for the 8 ball. You get something like that. Now, if it's a perfect thing, you get something like this. But if they weighed the same, you should get a 1 in that last list. If they weighed exactly the same, the last one is the cue ball came in at 1, hit the other one, the cue ball stopped dead still, the other one went at 1. And so you perfectly exchanged all the energy from one ball to the other through a perfect impact. What happens on the table, I have no idea. I'm not sure. Does anybody know whether the physics department has a scale that's that accurate? They do? Oh, okay. Who has that, you think? Oh, okay. Huh? Does anybody want to do that next week? Okay. So we could split up and have a team. So we can go over and a bunch of us act like we're playing pool. 2 people steal the ball, run to the physics department. We all, just stand around talking to each other, and they come back. And then what we'll do is we'll shoot a little bit of pool. And then, do they serve lunch over there?
Yeah, they've got pizzas. They got like snacks.
Oh, do they? Are they okay? I mean, are they?
Like a personal pan.
Oh, okay. They're good. Okay. Well, so that way I can eat in the middle of class. Okay, so we'll do that. The thing is I really don't know. I played pool. That was the one thing I did. I mean, most people, you know, they went out for football or baseball or javelin or something like that. I played pool all the time. And so that was my deal.
Just so I understand restitution a little better, that's strictly the transmission of energy between the two generators.
Right. Let's
So
do.
So like, real quick, just, so say you had during this impact, you decided to actually interact in the form of the noise that it created, right? You had the
Oh,
values,
yeah.
and you had the value for that noise. It would go in the MCV, MB, and the MNV formula, right? So you would have the MVC1.
Okay, well,
and then that force.
let's add to it so maybe it makes.
But say, but if you're losing energy to sound, you can still have an E of 1, a restitution of 1, correct? Between the two balls, even though you're I'm just trying to understand.
Well, now, okay, so that's a good question because, first of all, I don't think there is a perfect impact. And so any energy that's lost or dissipated through that has got to be lost somehow. So that brings up a good point that somehow it's lost.
Yeah, and I was just curious if that affects the restitution term. Because it looks like, it basically looks like the way that you've got it set up right now, even though you're changing the restitution value,
Yeah.
you still have full conservation of energy.
Let's investigate that perfectly, because this is a conservation of momentum, kind of. Okay, so let's look at the conservation of energy. Okay, and let's look at it for the E values. Okay, so that's a really good question. And by the way, that question I'm almost always asked on a test is something like this. So let's slide down and let's do this. So before the impact, I had 1/2 m of the cue ball, velocity of the cue ball, 1 squared plus 1/2 mass of the 8 ball, velocity 8 ball initially squared. Now, I don't know why I wrote this thing tilting, but it's too late now because I don't know how to select it and make it tilt. So if I do that, I get 1/2. The cue ball was 1/7. This was 1 squared, and this was that, and this was 1/6, and this was 0. So the initial energy looks to me like it's 0.17 over 2. Is that right? Yeah, I don't know what that number is, but let's see. Let's make MATLAB tell me what that is. What is it? Okay, 0.085. Now let's do this. Let's go through and do the final energy. The equation looks exactly the same, except you're just putting a 2 there. But now, since I have these associated or function of E, I'm going to write this out. Well, here, yeah, I'll write this out in MATLAB, and let's see what happens here. So MATLAB, okay, 0.5. So this is the energy final, or energy 2. 0.5 times 0.17, right? That's that one, times VC squared plus F times 0.16 times V8 ball squared. Oh, I think I got to do that funny thing. Use power or element-wise thing. See, I think what happens is I got to do, see, since VC is a vector and V8 is a vector, I got to go back and do this. Whoops. Dot, what is it called? The dot thing. Okay, so there's my energy. Ooh, interesting. Oh, let me fix something. Okay, there's something to be fixed here. Because before, okay, I was doing, here's VC. I have to make sure I've got the right equation. VC is 0.16 over 0.17. Let me make sure. Okay, there is the correct VC. Where is the correct? Is that the correct V8? Okay, so the VC, the cue ball, if it's perfect impact, it's like dripping down the table real slow. This one's going faster. Now let me go look at the energy. And what you see is anything that's not perfect, so the same energy exists here than here, but then the difference between this and this is what you lose. You're losing energy somehow. And you can go down to the worst case scenario. And here, I know you can do, let's see, E is equal to, what's that thing called? Linear space. Or here, I'll just do it this way. Right. So here's E. Let me make sure I got E written. Oops. E is equal to E transpose. Let me go back and see it. So here's VC in that case. So here is the velocity of the cue ball from a bad impact, the E equals 0 should be, all the way to E equal 1. What do you think the velocity of 8 ball would be? Remember this number. Okay, let's go do 8 ball. Compare those two. They should. These are the cases where the cue ball sticks to the other ball. Now, the balls can't do that because if they stuck, they won't go across the table. But they would stick together. Now they're not sticking anymore, and this is the best case you got. Then if you look at the energy, there's the best to worst case scenario. So you started the whole problem with 0.085, and I guess that's joules. Because in that, he gave that to me in kilograms, right? Okay, so this is joules. And then I move backwards. This is the worst case scenario. So I lose a lot of energy due to it somehow sticking to the thing. So what I've always done in the past is given a problem where there's an impact and then there's an E, and then I say, okay, find the final velocity, of these two things. And then I'll come back and say something like, okay, what's the energy of the before and what's the energy after? And then I ask the question, what's the loss in energy? And that's just the subtraction of those two. And that kind of, to me, that sort of symbolizes this. This is conservation of momentum. This is conservation of energy. What's funny, this is extrapolating a little bit. When you get out of here and into other subjects, like, for example, fluids, there's certain laws that you have to consider that will always behave no matter what happens. Conservation of mass. Unless you've got a nuclear reaction, that's going to be always the case. This conservation of momentum always works. Conservation of energy not always works. Reason it not always works, because there's some loss. You just identified the loss of the ping that you hear from the acoustic noise. That energy comes out of the system somehow. When you get into fluids, what you'll notice is those are used a lot. Conservation of mass. Mass in is equal to mass out. Nobody's in thermo yet, are they? Yeah. Oh, you are? Okay, so y'all have done mass in. So that always works unless there's a nuclear reaction happening there. And then if you're doing that, there's probably a nuclear course to take after that. That always works. The F is equal to MA kind of thing, or MV, all the MVs initial equal to all the MVs. That always works. Energy You could have some object or some fluid going through something, and you want to say the energy out. So, well, there's going to be some losses in there somewhere that you have to take account. If you took and accounted for every single loss, it would add back together. What I mean by that is you could say, okay, the energy between here, like the second one, okay, and where, okay, so you lost the difference between these, which is some number, 0.009 something. So you lost that energy. If you knew where it went, you could account for it. You could say the initial energy minus the loss due to noise is equal to the final energy. But sometimes you can't really identify that. You don't know what that is. You can't figure it out. And that's often what happens in labs too. You know, there was a thing years ago about cold fusion. And there was all these people were doing this. Oh, cold fusion works. Cold this, and they had papers running around. People were all a dither about it, all this sort of stuff. And it turns out that they couldn't account for losses of energy. It wasn't momentum. It wasn't mass. It wasn't anything else. What they were doing, they were weighing stuff and trying to figure out, well, this energy we got out of it, did it change the mass of anything? And had different things. It became a big feverish thing, and then it just dissipated. And it's still around apparently, but it's so small and that it doesn't. It's not a big deal. The latest thing. Have y'all heard about the plastic-eating bacteria? That came up. I guess I read it yesterday. Now it may have came up 4 or 5 days, or maybe even a week or two ago. It is kind of cool. Huge business opportunity, especially if you're in environmental engineering. Which, if you want to know the highest salary of any engineer in the last 10 years, on average, it's environmental engineering. Because it used to be, let's find all this oil. Now we found it. Now we made all this plastic. We got all this trash. What do we do with it? Let's call it the environmental engineering. So you got trash everywhere. These people are figuring out how to do away with it. So they're kind of like a combination of a biological engineer, environmental, you know, they take care of a lot of stuff like that. But I read that article yesterday. It's kind of cool. So I think they said they found it in a dump in Japan. Some sort of bacteria that was eating the plastic and feeding off of it, and had some sort of chemical thing in it, you know, with all these big words stringed together. I took organic years ago. Heptane, butane, all that sort of stuff, you know. But hey, you know what time it is? You knew. Okay, I'll generate a I'll generate that thing. Okay, so you were asking for a study guide, and I was going to give you a sheet, but I'm not one sheet, but a couple sheets. But I think I'll just put it on the, yeah. Huh? That is a good question. It's sometime during that finals week.